ready to go?
Yes, we are next now with live with the next talk, which will be Matt Bentley. We have a bit of an echo, so I'll just ask you to get started.
Okay. Hey everybody. So title of the talk is Performance Matters, New Tricks for Old Dogs. If you're not familiar with the English phrase, it's you can't teach an old dog new tricks, so that's what we're going to attempt to do today. So all of the stuff that we're covering is stuff that I've kind of done in the past or this year or that sort of thing, just a kind of collection of stuff really. So we're going to go through 3 algorithms, 3 containers, and 1 issue which will remain mysterious until the end. So the first algorithm is PLF reorder arrays, which is a portmanteau of reorder plus arrays. If you're not sure what a portmanteau is, it's a combination of 2 words to form a new word. Second one is PLF list, which is a more cache-friendly or unrolled list. PLF indie sort, which is a portmanteau of indirect plus sort. PLF queue, a faster better queue. PLF stack, a faster better stack. And segtors, which is a method for random access in containers with multiple memory blocks and a growth factor. That's the literal name of the paper that I wrote, which is on the website plflib.org. All of this stuff is on plflib.org. Now, so first thing, PLF reorder arrays. Evolution extension of the swap and pop idiom. Most people are familiar with the swap and pop idiom. If you're not, basically if you've got a vector or a deque and you want to erase from anywhere but the back of the container or the front for deque, and you don't care about element reordering, what you can do rather than erasing and then having all the elements reallocate backwards by 1, which can be quite slow if you've got a very large or non-trivially copyable type, or just a large number of elements, is you can swap the back element with the element that you want to erase and then pop the new back element, which is pretty fast. Most people nowadays realize that instead of swapping and popping, you can just move and pop instead, which saves a bunch of instructions and also means that you don't have to allocate a temporary buffer for the swap. So this is basically what that is, but templated, and it covers all the sort of odd cases. So it's only useful if you don't care about element order, basically. What I found was that this pattern also extends to range erasure, provided that you take into account the potential overlap between the range that you want to erase and the back range. You've got to truncate that range. And it also extends to std if type functionality. Basically, it ends up being the equivalent of range erasure using the return from std partition with an inverted predicate as the beginning part of the range, but without all the unnecessary swaps and copies that you get from partitioning operation. So I'll just give you some performance results. So through this talk, going to be giving a few sort of benchmark averages because don't have time for individual benchmarks. Only got an hour. So everything that I'm giving in is an average across numbers of elements ranging from 10 to 1 million with 4, 8, 40, and 490 byte types. For reorder arrays, the performance more or less linearly scales with the size of the type and the number of elements, and also potentially for some elements, whether they're non-trivially copyable, etc. So singular erasure averages about 1 million times faster than arrays position with a minimum of 10%. That's like 10 4-byte elements, for example, and a maximum of 25 million%, which is like 1,490 byte elements, right? Range arranger, not quite so fascinating. Averages 12,000% faster than standard ordered erasure with a minimum of 20% and a maximum of 77,000%. Scan erasure averages 38% faster than std arrays if, with a minimum of 0% and a maximum of 180%. So that gives some good reasons to use this over regular erasure if you don't care about order, right? So range erasure, I'll just go briefly into how that's done. So we've got the area that we want to erase in the middle there, and then we've got the area at the back that we want to move into that place. we've got an overlap, and basically the overlap, nothing happens to it, it just gets erased. So all the area that isn't overlapped gets moved into place, and the area at the back gets erased. So that's basically it. So the advantage of using what I've done over rolling your own, I mean, you can just roll your own templates, it's fine. But just takes care of edge cases like non-movable and non-no-throw copyable types. In those cases, it will actually allocate a temporary buffer just in case there's an exception during copy processes, in which case it'll copy the elements that were going to be erased back into place. It's also optimized for deques, so it'll move and pop from the front instead of the back where appropriate. Highly optimized uses min copy when the type is trivial, that sort of thing. And it also introduces a range-based std erase if style unordered erasure. So basically std erase if for when you have a subrange of a container that you want to arrange certain types from rather than the entire container. So here's an overview of how that works. So you've got the range that you want to erase a certain type of element from. In this case, the 12. So we move elements from the back, but there's a 12 at the back, so we can't use that one. The 12 gets moved to where the 23 was, and we're pretty much done. That's kind of simplifying it a bit, but it gives the general idea. So that's the first algorithm of the day. Moving on to the first container of the day. This is PLF list, which is a cache-friendlier linked list. I did do a talk on this at Pacific C++ in 2017. That's on the website. If you want to kind of know more than what I presented here, you can go to that talk. Made one or two mistakes in that talk, but it's all right. So the first thing you might ask is, okay, performance, why do you care about a linked list? Fair enough. Linked lists do have some positive performance characteristics in some circumstances. They have the fastest singular non-back/front erasure in current std containers if done during iteration, or if you already have an iterator to the location that you're wanting to erase. They have the fastest non-back/front ordered insertion of std containers. They have the fastest sorting for large or non-trivially copyable/movable types. Why is that? It's because sort for std list doesn't move elements around, it just changes the values of the previous and next pointers that those elements are attached to. So when you've got a very large or non-trivially copyable type, it can be a lot faster to just be writing a bunch of pointer values rather than actually moving elements around and that sort of thing, even if the elements themselves aren't contiguous in memory. The next point is something that people use stdlist quite a lot for, including in open source projects like LibreOffice. Iterators and pointers to non-erased elements stay valid regardless of operations around them. For example, if other elements get spliced in or erased or inserted or a merge happens, the iterators and the pointers to the non-erased elements stay valid, which can be quite important if you've got, for example, multiple containers hosting different elements which point to each other, which is a quite common scenario in a game engine, but you probably wouldn't see stdlist used in a game engine for performance reasons. Linked lists also give you constant time splicing together of lists and of ranges within lists, which can be quite useful, particularly if you're returning stuff from concurrent functions and you want to combine the data. And it's relatively easy to create concurrent versions or to use linked lists in concurrent scenarios, simply because the arrays and insert operations don't have a lot of side effects. So they write a couple of pointers to the previous and next nodes, but that's about it. So, PLF list versus std list. Performance averages 293% faster insertion, 57% faster erasure, 17% faster iteration, 77% faster sorting, 70% faster reversal, 91% faster remove-ish, 63% faster unique, 811% faster clear, about 1 million times faster for trivially destructible types, 1200% faster destruction, 63 100% faster for trivially destructible types. We'll get to that. And 20 to 24% faster performance overall in ordered use case benchmarking, i.e. when you're inserting, erasing, and iterating on data in a container over time. So just to circle back to clear and destruction, so 1,000,000% is a lot, so you might be asking yourself, why? Well, for a linked list, if you're wanting to clear, then you've got to go through and you've got to destruct all the elements if it's non-trivially destructible, but you also have to deallocate each of the elements. So you're going through memory, generally speaking, not contiguous in memory unless you're using an allocator, and even in that case, probably not entirely contiguous. So it's jumping all over the place in memory, and it's just doing a deallocation for every single node. PLF list allocates nodes in chunks rather than individually. And what that means is when you get a clear operation, if the type is trivially destructible, you don't have to process every node. You just say goodbye to all the memory blocks. You just deallocate all of them. So that's why it's such a high percentage. So how is this faster? How do we make it faster? As I said, it's got more contiguous storage because we're allocating elements and nodes in chunks. So down the bottom there, imagine those smiley faces are elements. And so that's how vectors and arrays are stored in memory. Most hashes, maps, lists, etc. are kind of all over the show in memory. And unrolled lists, deques, colony, hive, etc. are all in chunks. The second way that we get things faster is having smart erased node reuse. So rather than just letting those erased nodes sit there and not be reused, we keep track of them. And the last thing is that we have an indirect sort technique. So disadvantages. There are some disadvantages of this implementation. There's no singular element or range-based splicing between lists. There's only full container splicing. And that's because we're allocating nodes in chunks. So if you're splicing with stdlist, you can take all of these elements and chuck them into here. And it doesn't matter because they're just individual allocations. But with PLF list, you can't split a block in half because then you invalidate all of your pointers and iterators to elements, which means that it's not actually a splice operation anymore. It's more like a move or copy element operation. So you do have full container splicing, so you can take this PLF list and this PLF list and combine them. And you can also splice within the list. So, taking a range within a given list or an element within a given list and essentially reordering stuff. There's also more side effects for operations because you have to keep track of erased nodes and this sort of thing. So it's less straightforward to use in a lock-free or concurrent environment. So here's the basic structure of it. You have a vector of pointers to groups, which are basically a pointer to a memory block plus block metadata. The memory blocks start small, have a growth factor, and the maximum size is kept relatively low to allow for better reinsertion. We'll get to that later on. So, erased nodes, we can't reallocate backwards like you do with a vector or a deque, or you invalidate all the pointers to your elements, which is one of the reasons we use PLF, any kind of linked list. So what do we do instead? Well, okay, start off with, if we don't have erased nodes, here's what we do when we're inserting to some point in the linked list. So it doesn't matter where we're actually inserting to in memory, where our location is. We're just putting the element at the back of the list, and then we link up the previous and next pointers. Pretty straightforward. But not ideal, because that means during iteration you go, okay, this element, this element, this element in memory, and we're going all the way over here to the back, and then we go here, 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 etc. So not perfect. If we actually have erased nodes, then we can make this a little bit better. So when erased elements exist, first of all, we check to see if there are any erased elements in the same block as the element that we're actually inserting in front of, and if they are, we insert into that block. If not, we actually keep a previously stored pointer to the last block that we inserted into that had erasures. So we check that first, and if so, we reuse that. And if not that, then basically we scan from the block that contains the element that we're inserting in front of, and we scan out to the right and the left to the different blocks until we find a block with erasures in it. And you might not think that would be efficient, but it is, because essentially we have that vector of groups. So that means that it's all contiguous in memory. It's actually a very fast operation. And I did try a bunch of other approaches when I was developing this. And this combination of approaches had the best performance overall. So now if we've got these erased nodes, but there aren't any erased nodes in the block that contains the element that we're inserting in front of, then we basically scan outwards and we find an erased node and we insert to that. Pretty straightforward. And that having it scan outwards like that tends to increase cache locality, because when we're iterating, we're going, okay, this block, this block, this block. So even if we're here and we're here, and this block is in a different place to this block in memory, it doesn't matter, because during iteration, we're going to be going to that block next anyway, right? So it serves us to have that in the cache at that point. So even if we're iterating and it goes here, 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 this block, here, 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 and this, then this block, still more cache friendly, right? So just to go into briefly how we organize this reuse of blocks, we have a free list head for each block, which points to the last erased element in that block, and the next pointer for that erased element points to the previous one that got erased and the previous one that got erased, and that sort of thing. So that's how we keep track of stuff. So that's insertion and erasure. Lastly, we'll go into the sort technique, which is indirect sorting. So it has 4 phases. Gather phase, we create a temporary array of n pointers and linearly iterate over the PLF list blocks rather than following the sequence, because linearly iterating over the blocks is more cache friendly. We're not jumping all over the place in memory. And we fill the array with pointers to each element that we find in those blocks. Sort phase, we sort the pointers by the value of the elements that they point to via a dereferencing functor and std. It's actually std sort. I forgot to correct that. Anyway, via std sort. Using std stable sort wouldn't make any sense because of the way that we gathered the elements in the first place is already unstable. So then we have the scatter phase. We rewrite the previous and next pointers of each list node following the order of the pointer array, and then we delete the temporary array. So just to show how that works. So the sort phase, beforehand we have our array of pointers pointing to each of the elements. After sorting the array essentially points to the correct elements in sequence. So 1, 2 points to 3, points to 4, 5 points to 5, etc. And then when we get to the scatter phase, so we're actually going to move the elements now. Well, not move the elements, change the previous and next pointers on each of the elements. So we process the pointer array sequentially, and for every pointer at index I, we dereference to the node and set the previous and next pointers for that node to the addresses in the pointer array at I-1 and I+1 respectively. And we just do that right across the array, and then it's sorted. Then we just need to set the node pointed to by array index 0 as the front node for the PLF list instance, and the node pointed to by the last element in the last index in the array as the back node. And we're done. Which brings us to our next algorithm, which is based on that whole thing. It's called PLF indi sort. And this was basically me going, okay, this is kind of useful. How can I apply this to like all containers? And it's very similar. We have the same phases, but they operate slightly differently. The gather phase, we create a temporary array of instructs, of pointers plus indexes, and fill it with pointers to each element. We fill each index with its index into the array, so 0, 1, 2, 3, 4, etc. Sort phase, exactly the same. We sort the value, sort the structs by the value of the elements their pointers point to via the dereferencing functor and std sort. Scatter phase, we find move chains, we'll go into that, and swap the elements around until we are complete, and then delete the temporary array. So again, sort phase. Up the top, very similar to what we did with plf list, except that we've got old index there as well. After the sort phase, same sort of thing, so 0, 1, 1, 2, and then next one is 4. So basically, as soon as we encounter an old index that doesn't match its current index into that array, so in this case the first one is the 4 there, then we know that we've got something that needs moving around. Before that point, it's fine, we don't need to move anything around. So, this bit is kind of complicated. It actually took me a while going back over my notes and over the code to actually go, oh, that's how it works, okay. And I've explained it and simplified it as best I can, but it's still kind of complicated, so you're just going to have to run with it. Anyway, so scatter phase. Now what you'll see here are the move loops. So any move operation at the end of the day will end up with a certain number of elements that need to be moved around. And if there's only 2 of them, then it's essentially a swap, which is what you can see with the 2 and the 4 there. You know, the old index 4, that one points to the 3, old index 2, that points to the 5, and you can see that those 2 elements in the actual container need to be swapped around, right? And each move chain is exactly like that, but with more elements in between in the swap process. So what do I mean by that? Well, if you go up to the blue move chain there, 17, the 15, the 16, you can see that the 17 is pointing to the 15. That's where that needs to go. The 15 is pointing to the 16. So that's where the 16 needs to go, is into that place. And the 16 is pointing to the 17. That's where that needs to go, into that place. So essentially, but you know, we can't just copy those in place. We have to actually move them all around and keep a temporary there to store the first one that we moved around. Otherwise, we'll end up overwriting stuff before we have a chance to copy its original value into place. So essentially, it becomes like a swap operation, but with more values being swapped in between. So a move chain, right? So basically what we do, if we look at the simplest one that we've got there, which is the 4 and the 2. So we go to the 4, we go, okay, 4 doesn't match index 2 into this array, so this is something that needs to be moved. And we look at the value that it points to, which is the 3. We store that in temporary variable, and then we look at old index that points to 4, so we go to index 4 into the current array, which has the old index of 2, and we take the value that that points to, the 5, and we put that into the area in memory that old index location 4 points to. So basically we put the 5 where the 3 is, and then we go, okay, this one has an old index of 2, so we go back to 2 in the array, and we go, oh, that's the 4, that's where we started with. So now we know that we're at the end of the move chain, and we can take our temporary variable and copy it into the place pointed to by the last index that we processed, which is the one with the old index of 2, which points to the 5. So we take our temporary, which holds the 3, and we put it to where the 5 is, and then we're done. And then the last part of that process is that we write the new updated old index values to the old index. So where it is 4 becomes 2, and 2 becomes 4. That way, as we continue to process this array of structs, so after we go past the 4, we'll go to the 5, and we go, okay, that's part of a move chain, that needs to be fixed. After we've sorted that move chain, we'll go to the next one, and rather than the old index being 2, as it was before, it'll be 4. So we know that that one has already been sorted, it's already in place, and we don't need to process it again. So that's the basic rundown in very abstract terms. If you want the more rigorous pseudocode interpretation of that, it's this. So iterate over the pointer array until we find a move loop, i.e. the old index is not equal to the current index into the array. Move the element pointed to into a buffer variable. Store the current array index as des and also as start. Store old index as source. Move the element at array brackets source dot location to array brackets des dot location, where location is the pointer to the element in the original container. Copy source to dest, copy array brackets dest dot old index to source, and copy dest to array brackets dest dot old index. Keep on doing this until source is equal to start again, then move the element in buffer to array brackets dest dot location, and we're done. And go back to step 1 and continue processing the array until you get to the end of the array. So clear as mud? Great, we'll move on. So there are some technical optimizations that you can do to this. If you're doing this with a random access container, you don't actually require the pointer. You only require old index because the current index in that array of structs is the same as the index into the actual container. Old index, if you're sorting random access containers again, because you don't need the pointer, old index can be reduced in bit depth appropriate to the number of elements. So if you've got less than 256 elements, you can use an 8-bit old index, for example. And thanks to Bjarne for this one. This actually comes from a talk that he did earlier on in the year, and I watched it, and I went, so when size of t is smaller than, I'll just tell you what he said. So he was talking about sorting a std list, and he said, take the elements in the list, and we copied them to an array, and we sort the array, and then we copy the elements back. And I thought, yeah, that's a lot more straightforward than what I'm doing, at least for elements where their size of is smaller than size of t star plus old index. You know, if you've got std list of ints or a std list of doubles, it makes a lot more sense to just do that, copy the elements out to an array, sort them, copy them back in, than it does to do what I've just done. But if you've got non-trivially copyable types, or if you've got any type that's larger than a couple of pointers, basically, then my way of doing it saves a heck of a lot of memory and will be faster. So I incorporated Bjarne's technique into what I do with ND-sort. So it basically checks the size of the type and whether it's trivially copyable or movable, and it switches the algorithm based on that. So across 1 byte, 2 byte, 4 byte, 48 byte, and 490 byte types, and number of elements ranging from 10 to a million, 250 basically what I did was I took a basic bidirectional compatible intro sort algorithm, and I tried that on PLF Hive and PLF Colony, and compared that with ND-sort, and ND-sort is 250% faster than the bidirectional compatible intro sort algorithm. It's 28% faster than stdlist sort when you're using stdlist on types smaller than 292 bytes. Again, why is that? Because if you're sorting very large or non-trivially copyable types, it's much faster to just change the addresses on the previous and next pointers than it is to move elements around. But if the elements are smaller, it's much faster to do it this way. It's 146% faster than std-sort with vectors or arrays on types larger than 152 bytes, and also possibly some non-trivially copyable types which are also not movable. Same sort of thing if you've got reasonable sized types, you know, doubles, small structs, etc., then it's actually faster to just move them around than do this indirect process. Even though with this indirect process, most elements only end up getting moved or copied once, at most twice, which is with that the first element in the move chain gets copied out to the temporary and back. Yeah, so that's basically it. So it can be very useful depending on what your data type is and what type of container that you've got. Moving on. Next container, PLFQ, a faster adaptive queue. So why is stdq not adequate? It uses deque by default, and unfortunately deque implementations vary wildly because they're a little bit underspecified in the standard. For example, Microsoft's implementation, and this is not their fault, I'll go into that, it has a fixed block size of 16 bytes, which means that if you have a deque with any type that is over 8 bytes, essentially the deque becomes a linked list, which is not great. That's not their fault. They inherited that ABI from Dinkomware. Correct me if I'm wrong, somebody, who was the original company who supplied their STL implementation before they took it over and started doing it themselves. I know that they want to change that, or some people do within the company, but that would require an ABI break. But even if you're not using an implementation like that, like the other implementations have their problems as well. libstd C++ that has a fixed block size of 512, which is okay, but if you've only got a very small number of elements and the elements are very small, then it's problematic. If you've got a size of type that's very large, again, it can become a linked list. And libc++'s one gets around the ladder by having a very large block size, but it is a fixed block size of 4096 bytes, which means that if you only have a small number of elements or a very small element type, then you get way too much memory waste. So neither of these are optimal in any sense. But it's what they've got, and it's fixed in ABI, so they can't change it. So PLFQ adapts block capacities to reflect size. So it doesn't have that fixed size. It actually changes block capacities over time as the size of the container changes, the number of elements. So it's more appropriate to the use of a queue than deque implementations are. It also reuses blocks from the front to the back, unless the sizes change significantly, in which case it'll deallocate one of those blocks and get a bigger one or a smaller one. And I know that libc++, and I think Microsoft's implementation of deque also kind of does this, like reserves a block in place when it's been kind of popped off the front or whatever. I don't think libstd C++'s one does. It has iterators for debugging purposes, and the user can specify minimum and maximum block capacities. So benchmark averages ends up being 20% faster for 1 byte types, 10% faster for 4 byte types, 15% faster for 8 byte types, 40% faster for 40 byte types, and 65% faster for 490 byte types. This is benchmarked against libstd C++, so obviously you would get differences, and probably quite significant differences, when you're benchmarking against Microsoft's implementations for the reasons I just specified. The benchmark is a pump test, so elements are pushed and popped consecutively with the total number of elements just sort of fluctuating over time like an accordion. So that's that. PLFlist is, I think, possibly my first container because it was originally developed to be part of Colony, to be the thing that stored erased element locations before I realized there was a much better way of doing that. Then it split off into its own thing. And most of its code is very similar to PLFQ, which was developed later. So, again, why is stdstack not adequate? Uses deque by default as the underlying container for the adapter. Same problems there. If you use the underlying container as being a vector, that's much worse. The reason for that is that stacks only do three things. They push back, they pop back, and they read the top element. So vector has very good iteration performance. It does have good back erasure, pop back. But it doesn't have as good insertion performance, because when you get over capacity, you have to allocate to a new block. So deque is a lot faster for insertion. So deque's lack of need to reallocate elements upon insertion does help. Vector's iteration speed does not help. But again, there's no growth factor in blocks for deques. So PLF creates new blocks with a growth factor of 2. The user can define minimum and max block capacities. It also has iterators. So basic structure, and PLFQ is very similar to this. It's just an intrusive linked list of blocks. You could also do it as a vector of pointers to blocks as an implementation if you wanted to. It would be the same sort of thing, right? Benchmark averages versus std stack, basically about 80% faster for all types except for 90-byte types, and again, that's due to libstd C++'s deque issue, where the fixed block capacity is 512 bytes. So when you've got a 490-byte type or anything that's over 256 bytes, it essentially becomes a linked list. So that's why that one is so much different. The benchmark in question is total time taken to construct, push all elements, read and pop all the elements, and then destruct the container. Now, some of you may be thinking, yes, but couldn't we make a deque with a growth factor in its block and bypass all of this? The answer is yes, but then the question becomes, okay, if we want to do that, how would we make a fast operator brackets as well as fast iterator operators, plus, minus, plus equals, and minus equals? And this is where segtors come in. So name of the paper that I wrote is Random Access of Elements in Data Containers Using Multiple Memory Blocks of Increasing Capacity. And segtor is basically the prototype container that I made to test this theory, and it works. I haven't published the container because I would have to flesh it out more and do a bunch of optimization, and for some reason I haven't been bothered yet. So segtor is a portmanteau of segmented plus vector. The basic idea is you have a vector of pointers to element blocks. Then you create blocks with a growth factor of 2 and the total capacity of the container as a whole. So for example, if your first block capacity is 8, next one would be 8, that doubles the capacity, next one would be 16, etc. The initial block capacity must be a power of 2. Use these things together to calculate from the sequence index supplied to operator brackets both the block index in the vector of pointers and the subblock index of the element, so the index within the actual block itself. By using power of 2 block capacities with a growth factor of 2, we make the most significant active bit, i.e. 1 instead of 0, of the sequence index that we supplied to operator brackets relate directly to the block index. What do I mean by that? Well, okay, so here's how it looks in memory. Vector of pointers to element blocks. First block capacity is 4, next one is 4, next one is 8, etc. Pretty straightforward. Here's the concepts that you need to understand. Sequence index is the index of an element within a container. Block index, the sequential number of a given memory block in the vector of pointers. Subblock index, the sequential number of any element within a given memory block. Bitwise index, the index of a bit within a number when measuring from the least significant bit to the most significant bit. For example, if you have the number 3, then that is 1, 1, and then a bunch of zeros, right? So the most significant bit that has a 1 in it would be 0, 1. So location 1 is the bitwise index. So most significant active bit is the bitwise index of the most significant active bit of any given number, i.e. the highest bit set to 1. So in the case of the 3, that would be 1. So here is the pseudocode for the operator brackets algorithm. The first 2 lines only happen once during the container's lifetime. So we have M. is equal to the most significant active bit index of the first block's capacity, right? Then sh, which is our shift value, if m is equal to 0, then it's 0. If it's not equal to 0, then it is m minus 1, right? And we can pretty much get rid of m at that point because that's the last time we use it. Then in the actual operator brackets algorithm, we have j is equal to the sequence index, i.e. what is supplied to the operator brackets algorithm, bit shifted to the right by sh, our shift value. Then b, i.e. the block index, is equal to the most significant active bit index of j. And then k, basically if b is equal to 0, then k is 0. If b is not equal to 0, then k is equal to 1, bit shifted to the left by b, the block index, plus our shift value. And then s, i.e. our sub-block index, is equal to the sequence index minus k. Okay, so as an example, if we have our first block's capacity is 8, and we have our operator brackets, and it's supplied with 15, so we want to get to element 15 in the container. Now, if we think about that logistically, so first block capacity is 8, next block capacity has to double the capacity of the container as a whole, so that will also be 8. Operator brackets is measuring from 0, which means that 15 will be the last element in the second block, right? So m is equal to MSAB index of 8, which is 3. SH is equal to, well, is 3 equal to 0? No. So it is 1 times 3 minus 1, so it's 2. J is equal to 15, but shifted to the right by 2, which is 3. Block index is equal to the MSAB index of 3, which is 1. K is equal to, okay, is 1 equal to 0? No. So it's 1 bit shifted to the left by 1 plus 2, which is 8. And then our sub-block index is equal to 15 minus 8. So we have a block index of 1, so 0, 1, second block. And we have a sub-block index of 7, 0, 1, 2, 3, 4, 5, 6, 7, so it's at the end of that block, so it works, okay? Now, calculating MSAB index, because I've just sort of glossed over that there. Most modern processors contain an instruction designed specifically to calculate that. So you have the BSRL, BSRW instructions on Intel x86 CPUs, but where that's not the case, it's very simple to do code like this, where you just get your number, and you just bit shift it to the right until the result is equal to 0, and you add 1 for each point. So pretty straightforward. So the total number of operations is only going to be as large as the number of bits in that number. So here is our actual code for the brackets operator member function. So we get supplied our sequence index, that is index, and we have unsigned int block index. We supply that as the return value to our assembly instruction, which is BSRL. We supply 2 BSRL index shifted to the right by our shift value, which has been pre-calculated, and then we return vector of pointers to our blocks, and we index into that to our block index, which we've just calculated, and then we basically dereference to the actual block itself, and the sub-block index is our sequence index minus is block index equal to 0? No. Then bit shift 1 to the left by block index plus the shift value. So, clear as mud. So how does this all relate to deques? Well, it doesn't. You can just implement a segtor by itself and everything will be fine. You can just have a sequence container that just expands with a number of blocks in one direction. And the only thing that you have to do if you want to turn it into a deque is basically have 2 sectors and have them extending in different directions. Now, the illustration that I've got here, the sector on the left there, I've actually illustrated it kind of backwards to show how it would work. But actually in memory, it would be the reverse of that. But this is just easier to illustrate to make people understand it. So this is basically how you would do it. You would start with only one sector, which is the one on the right, and you just have one sector until such point as the user pushes to the front enough that it extends beyond the first block. So say you've got the one on the right there, and it's filled up the way that it is at the moment, and then you push front, and so you're going beyond the start of the first block capacity there. At that point, you would create a second sector, so the one on the left there, and you'd start inserting into that. So that much is pretty straightforward, and it's actually relatively easy to go back and forward. At any point in time, there's only ever going to be two sectors in that process, or one or two of them, right? I mean, you could start with one over here, and then you push front, push front, push front, and you end up with the one on the left there, and then you pop from the back, and pop back, pop back, pop back, and then it gets rid of the right hand one, and then you've just got the left hand one, and it could go back and forward like that. But at any point in time, there's only going to be two of these things. Now, complicates things a little bit if you want to use operator brackets, but basically what you would do is, if there's more than one sector at any given point in time, you basically keep separate size records for both of the different sectors, and if the sequence index goes over the left sector's size, if the left sector exists at that point, then you know it's in the right sector, and you do operator brackets calculation from the previous one. And basically all of your iterator operators, plus equals, minus equals, that sort of thing, can be implemented via the operator brackets operation. So you just, you've got your element, you work out what its sequence index is in the container, you add or subtract a value from that sequence index, and then you supply it back to operator brackets. Or you can do it a more complicated way, but that's the simplest way of doing it, right? Okay, so that ends that discussion. That is how you have a deck with multiple memory blocks with increasing capacities. I don't know if I'll ever get around to doing that. Maybe somebody else can. It's a little bit of a complicated operation. Anyway, food for thought. So, final thing of the day. This is the issue that I was referring to somewhat mysteriously at the beginning of the talk. It doesn't relate entirely to the rest of the conversation here, but it is a slightly different way of thinking about things. So it's not quite a new trick, but it kind of is. So this is my perspective. Time complexity is an implementation detail. What do I mean by that? Well, why do we care about time complexity? And it's all practical things. Like unless you're going into pure mathematics, if you are actually operating on a computer, which is a fixed bit of hardware with a fixed number of chips and this sort of thing, all of the reasons we actually care about time complexity are practical reasons, right? There's no theory to it per se. We care about performance, latency, and potentially resource use in some scenarios. So number of cores or amount of memory use, etc., as it relates to a fixed number n. Now, we won't go into resource use. That is a valid concern. It's not actually one that comes up that often, though, so we'll focus on the first two there. And the problem is that, since the earlier days of computers, RAM speed has increasingly been dwarfed by CPU speed, as almost everybody knows now. So that has decreased time complexity's relevance to the first two by making the whole process of what work is and what work the computer is doing a lot more complicated. What work the user programs is still, kind of the same. But anyway, what we have to look at is what really is time complexity. In my view, it's meant to be a measure of work done, right? Which is arguably correct from a very abstract perspective, but this is computer science. We're engineers. We're working on hardware, not something out there in the netherworld, so it's actually not abstract. And what actual work gets done is always hardware dependent. So how much work ends up getting done for a given operation that you supply, the operation itself may be a singular instruction, but it might inadvertently trigger a whole crap load of work, right? So whether a branch prediction fail forces a pipeline reload is hardware dependent. Whether a read from non-contiguous memory causes a cache miss is hardware dependent. Has it got a cache? Most of the time, yes. Some very rare processors don't have cache nowadays, but the vast, say 99.9% do for those reasons, because RAM speed is so much slower than CPU speed, right? And those are much bigger workloads for the hardware than singular instructions. So I think when we're talking about time complexity, largely we're kind of talking about the wrong kind of work, or in my view, we are weighing it perhaps incorrectly, right? So to look at work, we have to look at what is typically most important to performance and latency. And this is kind of my rough list, and it varies a lot based on hardware, don't get me wrong. But so this is a very rough thing. Cache locality of data, inter-memory speed, parallelism, allocation, deallocation, branching, although that's becoming less problematic as of more recent processors. Back in the Core 2 days, it was very significant. And lastly, I'd say time complexity. It's very rough, as I said. Given that that might be the case, therefore, it's only when the first four are not affecting performance significantly that time complexity becomes a strong concern, okay? So, but cache locality, parallelism, branching are all considered hardware-based implementation details and not something that we talk about in the standard or in computer science in general, right? Generally speaking. I'm sure some professors and computer scientists, universities do, but the reasons why we care about those things are the same reasons we care about time complexity, aside from potentially the resource use, performance and latency. So it's only typically once they're eliminated that we should be worrying really significantly about time complexity. And the fact that we have to consider that based on our hardware, whether time complexity is actually relevant to the performance in our scenario, is what makes it an implementation detail in my view. And you can go back and forth with the semantics, but this is the way I'm looking at it currently. I might change my mind. So examples of this. So the performance improvement of reorder arrays over regular erasure improves based on size of, not just the number of elements. And this is not purely down to the cost of copying, but also the cache locality of the larger elements. So if you have, 1 million chars, for example, and they all fit in memory, obviously the reallocation operation caused by regular erasure on a vector from non-back is going to be a lot less than if it's a larger element that doesn't all fit in the cache. Both std-list sort and std sort have O in log n complexity, but that has nothing to do with their performance, which is entirely dictated by the algorithm and cache locality. And that's why with indi sort, it can be a heck of a lot faster to just copy the elements out into memory and then std sort them and then copy them back, right? Even though you're essentially, you're not changing the pointers, you're actually moving elements around. PLF stack and std dec insertion are both O1 amortized, but one of those gets faster over time due to the lower number of allocations because PLF stack has a growth factor in the number of blocks. More examples, PLF list insertion is at worst ON in the number of memory blocks in that container, but it doesn't stop it being 293% faster than std list insertion, which is O1, due to the number of allocations being low and the memory block metadata being contiguous in memory. For many sets of data, it can be faster to do the same operation many times rather than to store the result once in memory due to memory speed, i.e. ON can be faster than O1, but typically the N is fairly limited. Strong example of this, Doom 3, the game, the BFG edition of that, which they basically rewrote the engine 10 years later after the initial release. There's some technical notes for that you can look up online, and one of the things that they found was that they were pre-calculating these meshes and then for each object, and then storing those meshes in memory and then reusing them for each rendering pass. And what they found was that it was actually faster to just recalculate that mesh for every single rendering pass, and from memory there could be quite a number of rendering passes, than it was to store it once in memory. And that's because the processors had changed so much, and the difference in performance of memory speed versus CPU speed had changed so much that the pre-calculation and storing it, retrieving it from memory was slower than just calculating again. And lastly, differences between alternative skip field methods in PLF Colony, one of which is O1, the current one, and one of which is ON in the number of elements in that particular block, made about 1% performance difference overall. So yeah, anyway, that's basically it. So why are we so hung up on time complexity? Hung up is a bit negative. Perhaps I should be saying, why do we put so much emphasis on time complexity and we don't tend to talk about the other ones so much, particularly when we're dealing with kind of standards issues and this sort of thing? I think the reasons are largely historical. Back when C++ started, time complexity was a much, much more relevant concern. The effects that we've had that have changed over the past 30 years with CPUs and memory speed and blah, 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 have been gradual. They've happened over time, whereas time complexity is sort of something that stays static, but its relevance does not stay static, and that's the problem. But it's got institutional entrenchment, so we kind of have to talk about it. And also time complexity is a little bit fun to talk about. Like I kind of compare it to musical notation, understanding music theory and that sort of thing. It doesn't make any difference to how good the music sounds at all. It's not relevant to how good music sounds, but it can be fun to talk about and fun to understand. So, and time complexity is not irrelevant to performance. Like if you get all your ducks in a row, if you get everything lined up, if you get a vector which has all your data and it's all contiguous in memory and your items are, trivially copyable and you're not doing a lot of branching and you're not doing a lot of deallocating and allocating, this sort of thing, then once you've got that scenario, then it's all based purely on time complexity and everything just sort of scales according to plan based on that value of n. And that's great. And that's a very real concern, and it's a consistently useful concern. But what I'm kind of not okay about is the fact that we spend and waste so much time talking about time complexity as if it's the be-all, end-all or something like that, or has this huge relevance compared to the other things, and we don't talk about any of these other things. So I think either we should be talking about all of these things, or we should be talking about none of them. Because at the end of the day, it's just another implementation detail to consider once you've got all the other stuff out of the way, sorted, thought about, etc. And that is my talk. Thank you everybody for listening, who listened. All of the technologies and blah, blah, blah that I've discussed are on plflow.org. And I wish you all a great day. Thanks for sitting through till the end. Bye.
Thank you for your talk, Matt.
Thank you.
It's been great. And if there's any more for discussion and question, please join the launch table with Matt and have a discussion with him about more of the things he mentioned. Great talk. Thank you.
Cool. Thank you.